Let's look at solutions of the wave functions for the hydrogen atom. So ultimately we're interested in the three-dimensional wave function involving the r, theta, and phi coordinates. But for right now, let's just focus on the radial coordinate with the function r of r. Well, actually at some point we needed to make a change of variables to make the calculation simpler, and so we changed r of r to u of r over r. So this function u of r we end up working with, but it turns out that that wasn't really enough for us. And so we had to change from the u of r function. We needed to change variables into the variable rho. And we pulled out the small rho and large rho behaviors. And then we had left over this unknown function v of rho, which took care of the intermediate behavior in between the small rho and large rho limits. By the way, rho was written in terms of the energy levels of the electron in the hydrogen atom. And if you plug in what those energy levels are after we figure out what those quantized energy levels are, then rho turns out to be really simple in terms of r. Namely, rho is just r over Na, where n is the number of the energy level. And a is this Bohr radius, something around 0.5 times 10 to the minus 10 meters, just a constant that shows up. Well, it turns out that the solution for this function v of rho is, well, it's kind of simple if you write it in terms of Laguerre polynomials. And so we wrote this in terms of Laguerre polynomials. So v of rho is this combination of the quantum numbers L and N. And that's a function of 2 rho. And the L function here is the associated Laguerre polynomial, which is itself defined in terms of the Laguerre polynomial. So this seems like a lot of nested information here, where what we need to do is figure out v of rho first, then we plug that in for u of rho, and then we plug that in for r, and then we have the radial solution for the hydrogen atom. So let's just do an example to see how that works. So let's take n is equal to 1 and L is equal to 0, the ground state. And let's calculate the function v of rho, see how this works in calculating that v of rho, and then following where it goes in the steps back up to the original function r of r, the radial function here. Well, so v of rho, we have to put n and L in the appropriate places for the Laguerre polynomial. And putting those in, it looks like what we need is the associated Laguerre polynomial L subscript 0 superscript 1. Again, that's a function of 2 rho, but for the moment, let's just take that as a function of x. So what we really need to do is figure out what is L01 of x. Well, we can use this formula here for the associated Laguerre polynomial. And the associated Laguerre polynomial is a set of derivatives of the Laguerre polynomial. So since we have a 0 downstairs, a 1 upstairs, it looks like p is equal to 1. And in order to get a 0 downstairs for the associated Laguerre polynomial, q must also be equal to 1. So it looks like we're taking d by dx of L1 of x. Unfortunately, we have to go one more layer down to figure out what L1 of x is, and then follow this back up the chain. So the Laguerre polynomial L sub 1, by this definition, is e to the x, d by dx to the power 1, in this case, of the quantity e to the minus x times x. Okay, so I think we're finally at the lowest level here where we can actually calculate something. So let's do this derivative and see what we get. So if we do this derivative, it turns out we get minus x plus 1. You should double check that. Do that calculation yourself to make sure you get minus x plus 1 here. And now we can plug that minus x plus 1 in for L1 of x in the step right above this to calculate L01. So if we plug that in for L1, now we are calculating minus 1 times d by dx of minus x plus 1. And so that tells us that the Laguerre polynomial, the associated Laguerre polynomial L01, is just 1. Okay, so then when we put it back up here for the function v of rho, we just end up getting 1 here. It doesn't matter that it's a function of 2 rho because it's just a constant. All right, we're making progress now. We're pretty close to calculating the ground state wave function for the hydrogen atom. So let's keep going. Let's go back up the chain. Now that we have v of rho, let's plug this in and figure out what u of rho is for this particular value of n and L. Actually, what we should do is first write down what rho is in terms of r. Because we have the n value, n is equal to 1. So plugging n equal to 1 here, rho is just equal to r over a. Okay, now we can use that in our expression for u of rho up above. So u of rho is now r over a to the 0 plus 1, because it was L plus 1 there. Well, L is 0, so we just get a power of 1 there. E to the minus rho, well, remember rho is r over a, so I get e to the minus r over a, times the function v of rho. Well, v of rho was just 1, so I don't get anything there. So ultimately, for u of rho, I just get r over a, e to the minus r over a. So it's a relatively simple looking expression for the function u of rho. Let's go one more step up and calculate the radial function r of r. And the relationship there is I just have to take 1 over r times whatever I had for u of rho. And so taking 1 over r, the r's cancel. And so I just get something that looks like 1 over a, e to the minus r over a. Now I will point out that this isn't normalized yet. So we haven't normalized our wave function. This just gives us the functional form. But honestly, the functional form will get us pretty far here for the ground state wave function. Again, this tells us what the ground state wave function looks like. And so what we can do is we can make a plot of this ground state wave function and try and understand what's happening here. So if we make a plot of this ground state wave function, we see that the wave function, well, it looks like e to the minus r over a. So remember, you can't go to negative r since r is a radial coordinate. So we start at 0 and go from there. And so our wave function drops off exponentially fast from the origin. Now, this isn't quite the same as telling us where it's most likely to find an electron, because in order to do that, we have to look at the differential probability, the small amount of probability, which includes a volume element, but it's pretty close. And so we can see, in fact, that the wave function is peaked near the center of the hydrogen atom, and that's about what you'd expect for the ground state. You'd expect for the ground state the electron to be in as close as it can be. Okay, so I hope this was a helpful example on seeing how to use those Laguerre polynomials, how to calculate with them, and how to get that radial solution of the hydrogen atom.